So I will stop about mathematical modeling of systems, and then I will start showing how to analyze these systems. Okay, so normally, obviously, you can spend much more time on this mathematical modeling part. You can go through a lot more examples, or you can study different types of systems. But instead, I will spend more time on the analysis of these systems when you have the mathematical model. Okay, so you obtained the model for this system, and then the analysis part requires you to solve these equations to see how the system will respond to different types of inputs. Okay, so you choose a specific input. This can be a constant voltage, or it can be a changing voltage in the shape of a common waveform like a sinusoidal wave or a square wave, or it can be a random variation. Okay, so somebody can be changing the voltage randomly by just playing with the voltage source. So to be able to calculate the response of the system, you need to solve for these equations. But before saying anything about how to solve this, let's go back to a much simpler system. Okay, so here we have a relatively large system. We have three equations, and these are all differential equations, and they're all coupled, right? So we need to normally solve all these equations simultaneously. So let's go back to this simplest example, and let's talk about the solution of this equation on this example. So this is this spring mass damper system. The equation for this system is given by this second order differential equation, and that y you see there shows the position of the mass. So that is the y, and F is the external force you apply to the system, and the relation is given by this equation. So this is just a differential equation, right? And you saw how to solve differential equations. So let's remember how we can solve this equation. So let's start with a simpler case where there is no external force applied. Okay, so let's first to start with, let's assume that the external force applied is 0. So you don't apply any force to the system at all. So so without an external force, do you think the system will move at all? Well, there's only one condition for this system to move, and that is if you release it from a non-zero initial condition. Okay, so if everything is at rest, and if you don't apply a force, nothing will change. Then the trivial solution is y is equal to 0. Everything will stay in the original equilibrium state. But if you take this mass and either move it towards right or towards left, and if you add some energy to this spring, and then you release it from that condition, then there will be a motion, even without an external force. So that's what we will study first. We get motion if we apply initial deflection to the system and release it. So the solution we get for 0 external forcing is called the free response. So we call this the free response of the system. And the word free means that there's no external input applied. So basically, this is the differential equation we need to solve. A second order differential equation, and then some initial conditions are required. And since this is a second order differential equation, we need to know two initial conditions to be able to solve for this equation. And these initial conditions are the initial condition for the y itself and the initial condition for its first time derivative. Okay, so let's assume that the initial position is y0 and the initial velocity is y0 dot. Okay, so these are some constant numbers to be supplied. Okay, so hopefully you all know how to solve for this equation, right? It's just a simple second order linear ordinary differential equation with constant coefficients. And if you remember from your differential equations class, the solution to this equation depends, in fact, on the values of these coefficients. Okay, the solution can have different forms depending on what the values of those parameters are. So the values of these numbers are important. So obviously you need to know what they are to be able to find the solution. And the conditions are written here. So I'm not sure if I need to copy everything from here to the other file, but so that's what I have been doing. So let me continue that. Okay, so if there is this condition satisfied for these parameters, which says that the B coefficient, and this B coefficient is for the damping, the constant for the damper, and if it has a value which is greater than a certain amount, which that certain amount is given by this relation, then the solution will be in this form. Okay, in the solution you will have two exponential terms, and these exponential functions, the coefficients here will be given by this expression. Okay, and so these are all depend on the system properties, the damper constant, the mass of the block, the spring constant, and you put the numbers here, you find two values, A1 and A2, and there are these coefficients, C1 and C2, and if you want to calculate those coefficients, you need to use the initial conditions. And to find these coefficients, you need to apply the initial conditions. You first insert 0 for t, and then for the output, the value should be equal to y0. This was given. So here you have one equation for C1 and C2. To use the second initial condition, you take the derivative of the solution. So you differentiate this function with respect to time, and then you insert the initial condition for y dot, and you get a second equation. And from these two equations, you can solve for C1 and C2. Okay, and if you do that, this is what you get. C1 and C2 are given by these parameters. So that's it. So you have a solution, right? So you insert these C1 and C2 parameters, and then A1 and A2 into this expression, and that will give you how the position of the mass will change when released from these certain initial conditions. Okay? So maybe I can show you how to plot the results in MATLAB. So let me. Okay, so I define these variables for the system parameters. So I choose these. So these should have compatible units. So mass should be in kilograms, for example. This should be newtons per meters. This should be in newtons per meter per second. So I don't need this at this moment. First, I calculate these A1 and A2 numbers, and I just use this expression. Okay, I use this equation to find A1 and A2. Then I find C1 and C2, but for this I need the initial conditions. So let me I assume that the initial position for the mass is 0.2 meters and the initial speed is 0.5 meter per second. And these are the coefficients for the solution of the differential equation. Then I can just plot the results, and I want to first I define this time vector. So this means I want to plot the results in the time interval from 0 to 10 seconds with an increment of 0.01 seconds. So this is my time vector. This is the output function, and that is the same function as, so that's this function, C1 times e to the power A1 times t plus C2 times e to the power A2 times t, and all these values are known. So the C1, C2 coefficients were defined here, and A1 and A2 were defined here. Okay, next I should make a plot. So I can just say plot T and YA. So if I run this, I first need to save it. So this is the response of the system. So the horizontal axis is time. So let me add those. X label should be time in seconds, and the Y label should be the position of the mass. So let me just write that as Y, and it should be in meters. So this was the initial point at t is equal to 0, and when I release it, this is how it moves. So it keeps moving towards right, and then it comes back to the equilibrium point, right? So if you imagine what that means, the block starts at position 0.2 meters with a positive speed. Remember, the initial speed was 0.5 meters per second. So initially it is moving with a speed of 0.5 meters per second. But it slows down quickly. That's because both the spring and the damper are trying to slow it down. It slows down and then it starts moving towards left and then comes to rest at the equilibrium point. So if you look at the graph here, the initial speed must be 0.5 meters per second. So that means if you take a look at the slope here, you should find 0.5 meter per second. So 0.5 meter per second means that in 0.1 seconds it should be 0.05 meters, which seems about right, right? So I'm just trying to make sure that my result is correct. So let me just insert a line here. So I'm starting from the starting point, and this line should be tangent to the graph at the starting point. This seems about tangent. And in 0.1 second it should reach 0.05 meters, which is almost correct, right? So this should be the exact value, and I think this is the exact tangent. So anyway, the result seems to be correct. That's what I was trying to show. Okay, but so maybe I shouldn't have shown you this first. So let me remind you that this solution is valid only if this condition is satisfied. So I must have checked this condition first. So let me check this condition is satisfied or not with the values I selected. So the value of the b is 5, and there should be square root of 4 times m times k. Okay, so it is greater than this value, right? So this is the correct solution. So this is something I must have done before I did all that. Okay, so let me try it with a different initial condition. Now let me try it with a negative speed. So let me make this negative. That means the block starts from the same initial condition, but with an initial speed towards left. So let me run this one more time. So this is what I get. So we don't have this change of speed. It starts with a negative speed and it continues that way, and it again reaches the equilibrium point of 0. And this initial slope here again should be minus 0.5 meter per second. Okay? So this is how you plot the result once you have the solution. So remember, we obtained the solution analytically by solving the differential equation. And then once we have the solution, we just use MATLAB to plot the result. So normally we can use MATLAB to obtain the solution as well, which is what we will do later. But right now we found the solution manually by solving the differential equation, and then we just use MATLAB to plot the result. Okay? And here you see the different results, but now we just solve similar plots on MATLAB directly. Now let's see what happens if that condition is not satisfied. Okay, so if that condition is not satisfied, and if the value, the constant for the damper is smaller than this critical value, then the response will be different. In that case, in the response, instead of having two exponential terms, you will have one exponential term multiplying this second term, which contains sine and cosine terms. So in this case, you expect to see some oscillations because of these trigonometric terms, right? So the solution is given by this equation. Again, there are two coefficients, C1 and C2. And just as before, we find the values for these coefficients using the initial conditions. And if you do all of that, you find that the initial conditions these coefficients depend on the initial conditions through these two expressions. I don't really have the code for that ready, but let me just quickly code it here. So the A1 and A2 are again given by this expression, but this time you will get a pair of complex numbers. Okay, so in the first case, due to this the other condition, this would give us a real number, and then both A1 and A2 were real numbers. But in the second case, due to the square root term, we get a negative number within that square root, and which will give us imaginary numbers. And as a result, the A1 and A2 pair is now a pair of complex numbers. the A here is the real part, the B is the complex part. Okay, so this is what you see. So the A1, A2 is given by this expression, A plus minus J times B. And A and B are used in solution. A is here in the exponential term, and B is appearing in the cosine and sine terms. Okay, so first let me make B smaller than this critical value. So let me just choose 2. If I make the value of B 2. So let me run this part only. I'm not executing the entire code. I'm just evaluating the selected part. And let me find these A1 and A2. And as you see, both A1 and A2 are complex numbers. This time A is the real part of these. And B is the imaginary part. So let me insert these into my code. So let me use the same initial conditions, and this time C1 and C2 values change. C1 is equal to Y0, and C2 is given by minus A over B times Y0 plus 1 over B times Y0 dot. These are my C1, C2 values. And now my solution is, so let me call this YB. E to the power 80 times C1 times plus C2 times sine BT. Okay, so this is the response for the second condition. It should be 1 over B, right? Okay, so these are the errors you will frequently get. So I wasn't careful in this multiplication. So this is a column vector. I try to multiply that with another column vector, which is not allowed. So I need to make the multiplication of the corresponding elements. For that, I need to insert this dot here. Okay, so this is the response for this second condition. I start from the same initial condition. But this time, remember, in the first case, it was going to 0 immediately. This time, it passes 0, and it comes back, and then still finally approaches 0. So maybe I should plot both responses together. But of course, to be able to do that, I need to change these C1 and C2 values. Okay, so I just quickly took it back to the original state. So this was the first condition. The B is greater than the critical value. The response was this. And now the second, I saved it with a different file name. Let me run the file for the second. And let me plot the second response in red. Okay, so if the damping constant had a value of 5, the motion is represented by the blue curve. But if the damping constant has a value of 2, then the response becomes like the red one. And they both start from the initial point with the same initial slope, which shows that the initial conditions were really the same. Okay? So if you want to see the response for a different value of B, so let me make B even smaller, but it should still satisfy this second condition. So I shouldn't make B large, but I can make it smaller. So let me make it 1, and let me make the plot with black. Again, starts from the same point with the same initial speed, but this time the response oscillates even more, as you see here. Okay? And let me make it even smaller, 0.5. Let me change the color so that we can see what's happening. Let me use green. It's hard to see green here actually. Let me use magenta. So anyway, this is basically, I'm just simulating this simple spring mass damper system, right? I'm giving it initial conditions. I'm choosing system parameters. So let me choose a different mass value. For example, let me make the mass double the mass, or double the original mass. Let me make it 2. I'm really out of colors here. Let me use blue again. Okay, so if you change the mass, this is how the response changes. So let me remove these old ones. So the response with mass of 1 kilogram is this purple one. Without changing any other parameters, if I just change the mass, so if I add 1 more kilogram of mass to the same block, then the response becomes the blue one. Okay? So this is just the free response. There is no external force yet. I'm just simulating the system with non-zero initial conditions. So I just bring the mass to a certain point and then release it with an initial velocity. So I just give it an initial velocity, and then this is what the response looks like. So let me set the initial velocity to 0 instead of, so that means I'm releasing it from the initial point with 0 velocity. And let me show you how the response looks like with black color. And here you see that the initial velocity is really 0. So these are important details, but it tells you whether your result is correct or not. If you don't see a 0 velocity, initial velocity here, then that will certainly mean that something must be wrong in your code. But we see that the initial slope appears to be 0. It's close enough. Okay, now this is enough for the free response. Well, we get a special case when the damping value is 0. You know, the damping value should satisfy this inequality. here I tried 0.5, but if I make it 0, which means there is no damper in the system at all. And when you plot that using red, the response with 0 damping coefficient is the red one. So anyway, and I shouldn't use negative numbers at all because they're not meaningful. Just like negative mass doesn't mean anything, right? No object can have a mass with a negative value. Similarly, the spring and dampers, they are physical elements and they have to have positive values. A negative spring doesn't really mean anything, so I should limit myself to positive values only. Okay. Now this is the more interesting part actually. The finding the response to initial conditions is really easy. But what's more interesting in reality is when the input is supplied with an external input. So this time we also need to find the response of the system to external inputs. This time let the initial conditions be 0. So this time, to make the problem simpler, I'm assuming that the initial conditions are 0. We're starting from 0 condition. But we have an external force. And this is called the forced response. The previous one was free response. This is called this is the forced response. So the solution will obviously depend on what f is, right? I mean, if you consider a constant number, you can find the solution. If you consider a different constant number, the solution will be different. If you consider a changing input, an input that changes in sinusoidal form, there will be a solution to that. If you consider an input that changes as a square wave, the solution will be different. So every input you can think of, there is a solution, and that solution will be different if the input is different. And since you can have infinitely many choices for the input, there will be infinitely many solutions for each input you want to calculate the response for. So that's why calculating the forced response is not an easy thing. Okay, so you need to find the input, you need to know what it is, and then you need to solve the differential equation for that input. And every time you want to simulate the system for a different input, you need to solve the differential equation again, corresponding to that input. Okay? So obviously this is really not an easy thing. So what we can do is we can start with some simple inputs instead of some randomly or arbitrarily changing inputs. Let's consider a step function. Okay, so let me insert an explanation here. Solution for the forced response depends on the input applied. For every different input applied, there exists a different solution. So the equation needs to be solved again every time the input changes. Let's start with perhaps the simplest input signal. The simplest input signal is just the constant number, okay? But since we assume that the initial conditions are 0, initially the system is at rest, and at t is equal to 0, we start applying the input. Okay, so the input is a constant number, but it's in the form of a step function. So let me show you what the input is. So the input is a force here, F. So this is the 0 point. So prior to 0, the input is 0, but at t is equal to 0 instant, I start giving a constant force to the system. So the magnitude is given as 1 here. So the magnitude is 1 newtons. Okay, so this is my input. Okay, so do you know how to solve the differential equation for that given input function? Well, to be honest, I don't know it myself. But I found that the solution is this thing. Well, if you don't believe me, I'm sure you can find the answer yourselves. But so this is the solution to the position of the mass as a function of time when it is released from 0 initial conditions and a force with a magnitude of 1 Newton, a constant force with a magnitude of 1 Newton is applied to it. And this is what the solution looks like. Okay? So imagine this is the simplest possible system mechanical system you can have, with just one mass, one spring and one damper. No initial conditions. You start from 0. And the simplest input you can imagine, just a constant number. And the solution looks like this. So imagine making it more complicated. Imagine adding initial conditions to this or adding some random inputs. Okay? So what I'm trying to say is the solution of these differential equations is not an easy thing. Also, imagine trying to do this for our previous example. Try solving these set of differential equations together for an external voltage applied, external constant voltage applied. Believe me, it's not going to be easy. You don't want to do that. What we do today is, obviously we can solve these things numerically very fast by using a computer program. These differential equations can be integrated numerically in time, and that way you can find the answer very easily and very rapidly by applying this numerical solution, which is what we will do in practice. So if you think about any simulation program, any simulator for an aircraft or a simulator for a mechanical system, it will certainly be using numerical integration methods. So you just take the integration of these equations numerically. So this is why you're taking this 305 course, by the way. So you're all taking that course, right? 305. So in that course, you learn how to do these numerical integrations. So you will be doing a lot of homework problems related to integrating differential equations numerically. We do that in controls as well. We use MATLAB to solve for these equations, and it's very straightforward. But 100 years ago, they didn't have any computers to do all these things. And today, even though we can solve these things, we want to analyze these things more systematically. Okay? So remember what I did here. So what I did here is I tried different values for system parameters to see their effect. Okay? So based on here, I can tell you that if you increase the mass, the frequency of oscillations will change. Or if you change the damping number, certain properties will change. If you do numerical solutions, your only chance is trial and error. You simulate it, you look at what happens, and then you try to draw some conclusions. But for a lot of different things, that's not acceptable. You want to have a better understanding of the problem. Okay, so you want to be able to say, if I want my system to fly like this, if I want my aircraft fly like that, I don't want to find what I should change by trial and error. I want to say, okay, this is what I should do. I should make my horizontal tail bigger, for example, or I should make my wings like longer. Okay, so to be able to say these things, we still need to find, we still want to solve for these equations analytically. So numerical integration will not answer those questions. So what we do is, we still care about solving for these equations manually, but instead of trying to solve them in time domain, we use a very powerful mathematical tool called Laplace transformation. And as you will see in our future courses, Laplace transformation makes solving for these equations very easy, and it gives us analytical solutions, and it gives us what we need. So it gives us the connection between the physical properties of the system and the actual behavior. So that way we will answer the questions I mentioned earlier. So that will give us how we should change our system if you want to change its behavior. Okay? Any questions? Okay, siz zaten ders kafanızda bitirdiniz herhalde. Böyle birkaç dakikada bir uğultu başladı.